9.4. Comparing two population proportion. Independent sampling. We have two population, population 1 and population 2, or could be the same population but in different conditions, different years. In this population we have a proportion, this proportion will be P1, that is the population proportion, and this other one will be P2. Then how can we estimate or how can we compare these two population proportions? It's very easy. We'll take a sample, and in those samples we are going to compute my sample proportion and the difference between these two sample proportion. If these two samples are big enough and representative sample, this difference will be close to the difference between these two parameters. Very simple. But let's analyze what happened with the sampling distribution and how is the distribution of all difference. Let's start. And first of all, we studied in the chapter 7 the sampling distribution for all sample proportion. In this is the population, we have all children, and if the population have that proportion, then all of these children must have approximately the same proportion, and the distribution of all of these sample proportion will follow a normal distribution when my sample size is big enough. Remember, my sample size is big enough for proportion when NPQ, N1, P1, and Q1 is greater than 10. Given this condition, we can assure that the distribution for all sample proportions is normal distributed, and the center of the distribution will be the true parameter, the true proportion of the population. That is the sampling distribution for proportion. And the standard deviation is given by the square root of PQ divided by N. That is for population 1. The same thing occurs for population 2. The population 2, the distribution of all possible sample proportion, all of them of the same size, M2. Then if this sample also is big enough is when my sample size times the population proportion times the complement of the population is greater than 10. If this condition is satisfied, then the distribution of all sample proportion, all of them with the same size, follow a normal distribution, and the center of the distribution will be the true parameter again, and the standard deviation will be given by this formula. But right now, in this chapter, we want to compare these two population proportions, this one and this one. Then we are going to select any samples, this sample, for example, and this other here, and we compute the difference. But how is the distribution of all possible two selections that we obtain from these two? The distribution of all of these different will follow a normal distribution when this condition and this condition are fulfilled. Then the distribution will be also normal for all difference, and that is the distribution for all difference. What is the center of the distribution? The center of the distribution will be the difference between the two true parameters. And the standard deviation, remember, the variance of this parameter, the variance of the distribution of this parameter will be equal the variance of the individual statistics. In this case, the variance of the distribution for all difference is equal the sum of the variance for the individual statistic P hat 1 and P hat 2. That is the theory, and that is the procedure that we are going to use. In the next section, let's construct confidence interval. But before that, the properties of the distribution for all difference will be normally distributed when my sample size is big enough. Both samples, the center of the distribution will be the difference between the two parameters. The difference between the two parameters is the expected value. The expected value of the difference will be the difference between the true parameters. And the standard deviation is given by this formula, and if the sample size are big enough, the distribution is normal. Then how can we compute my confidence interval? To compute a confidence interval, we have two populations, population 1 and population 2. Then we select a sample here and we select another sample here. Compute population proportion 1, population proportion 2, and the difference between P1 minus P2 actually will be approximately the difference between my samples proportion. But it's not exactly the same. We need to add or subtract an error. This error depends on the distribution of all difference. The distribution of all difference, this is the error. That is the error that we use to compute the difference between the two parameters. We use my sample statistics. Then we have a problem here. We use here population proportion for both populations. We don't know that. If we know that, we obtain immediately the difference. But we have to use my samples proportion to estimate this one. Then we need to substitute here my samples proportion instead the population proportion, and will be an approximation. The bigger are both samples, the closer will be that approximation. To test hypothesis about the difference of these two population parameters, it's the same procedure. Population 1, population 2. We take a sample from population 1 and we compute p hat 1, and we take a sample from population 2 and we compute p hat 2. Then, to test hypothesis about these two population proportions, normally there is a previous study or a reference value. Normally the reference value is the two populations are equal. Then let's see what happens if we change something. What happens with the population proportion? Most of the cases, the assumption is these two populations are equal. We will select from both populations two independent samples, and we are going to obtain the difference. Then suppose that this point here represents these two selections, and the difference between these two samples will be this value. Okay? Then how is the C-score? I have to transform this evidence in this Z-score. Z-score, remember, we use normal distribution always for proportion in this course. But we have also a problem here. We have the population proportion for P1 and Q1 here. When we test hypothesis, we make an assumption. What is the assumption? That these two population proportions, P1 and P2, no hat, P1 and P2, these two populations, the assumption is these two populations are equal. And we want to find some evidence that they are different. Then if we assume that they are equal, then we can substitute here the population parameter, here and here, using my sample. And let's assume that they are equal. If they are equal, we can select here, this p hat is obtained counting all values in this section and divided by my sample size. And what is the p hat 2? P hat 2 is obtained counting the value located here divided by my sample size 2. Then if we assume that these two populations are equal, then we can use these two samples and we can combine these two samples in only one, and we know that here we have x1 plus x2, and the sample size will be n1 plus n2 when we combine both samples. Then we can compute, or we can estimate, the population proportion, assuming that both are equal using this formula. P bar is equal n1 plus n2 divided x1 plus x2 divided by n1 plus n2. That is the population obtained when we assume that these two population proportions are equal, and we have these two samples. Because in all hypothesis tests, we assume that the two populations are equal. That is the meaning, the null hypothesis. When you say that the difference is 0, then you can assure that P1 is equal to P2. Assuming that the difference is 0, there is no difference, there is no change. And the alternative hypothesis is the negation of this one. Then we can substitute these values here, the population proportion here, we can substitute using my samples. And when I use my sample, I use P hat and PQ hat. where P hat is this one, P bar or P hat is the same thing. P hat and Q hat is given by this. Remember, you can rewrite this in this other way. P hat 1 minus P hat 2, then the variance will be the variance for the individual values will be P hat Q hat divided by N1 is the variance for the first population, and P hat Q hat divided by N2. But we transform this in this formula. It's much better. Then the alternative hypothesis is the negation of the null hypothesis. Null hypothesis states that there is no difference, and the alternative state there is a difference. The difference could be positive or could be negative, or we have a two-tail test in which we don't know, could be positive or could be negative. And the next step is to compare if this different, if my evidence, that is my evidence, this is my evidence condensed in one formula, then we need to compare this evidence, how far away is from the center. Remember, in the center we have the P hat is equal to P2 is my assumption. The difference, this difference is 0. That is the center. How far away is this evidence from 0? Then for that, we use the same procedure that we have used until now to obtain those critical values. This critical value should be obtained using alpha. Then this point and this point will be our reference point, either to the left or to the right, or in both sides when we are doing a two-tailed test. Or we can compute, instead to find critical values or reference point, we obtain the p-value of my evidence. The p-value of my evidence, this is my evidence, I compute the p-value. The p-value is the probability to get this evidence or one evidence more extreme in the direction of the alternative. Then we compute the p-value and we compare this p-value directly with alpha. That is the procedure. If p-value is smaller than alpha, we reject the null. If the p-value is greater than alpha, we fail to reject the null. We have insufficient evidence. And which condition these two samples must fulfill in order to do this procedure? First, the two samples should be randomly selected in independent manner from both populations. And second, my sample size should be big enough. This condition that the sample size should be big enough would be given using this inequality and this inequality for both populations. Or you can split this inequality in these other two. But I prefer to use this one, which are equivalent. NP, N1, P1, Q1 greater than 10 is equivalent to these two inequality. I prefer to use this that is condensed. And what happens if I select two samples that are not big enough? Then we have to use Fisher exact test. And we are going to study this in chapter 13. Let's stop here.